let me add some of the things that I skipped, which I understand more. So this one is saying that having this answer set programming or logical rules, we can create variants very easily. So that's what is Elabors intolerant. So saying, okay, if we have instead of Sudoku some other kind of Sudoku, they derive some new kind of Sudoku, no number repeats at the same relative position in this. All we have to do is add a few rules. I mean, this is actually good from the KR people point of view because you are writing by hand. But of course, from the machine learning angle, people are going to say, okay, who gives you this rule? Like, why you are involving humans to give these rules? So all those questions will be there. And then, oh, I think that was the main one. I covered all of these other ones. So June has made available the code, this paper, so you can find his code. And while preparing for this, I came across another paper. So this is very interesting paper, I think 2021 AAAI. This one. We haven't seen this before. So what this basically says is that it generalizes the NeurASP to saying that it's not necessary the ASP part. From this perspective, ASP part is not as important as that it's just the ASP part can be replaced by another logical module which has certain properties, for which you have a forward reasoning component and a backward reasoning component. So that's what this paper talks about, that even though for the rest of the talk, or presentation, we had ASP, but the idea behind this generalizes to other formalisms which have certain properties. And that's this paper. So let's see. So he's saying our work seeks to fill the gap by treating these two systems as black boxes to be integrated as modules into a single architecture without making assumptions on their internal structure and semantics. Instead, we expect only that each module exposes certain methods for accessing the functions that the module implements. The symbolic module exposes a deduction method of computing the function's output on a given input, and an abduction method for computing the function's inputs for a given output. That means it allows you to do the backpropagation. And the neural model, of course, is a neural model. So yeah, that's kind of there. There's some question, a chart. Okay, well, that's for John.
Yeah, we have a question.
Yes, please.
For the feminist addition problem, we referred that there are around 100 answer sets possible.
Right.
And for the Sudoku problem, you said that there are only 810 answer sets, I believe.
No,
if I'm mistaken.
10 to the.
So it will be actually it's very blurred, so that's why I'm worried about how does this work, because it means you have 81 and each of them can take 9 values, right?
Yes, 10 values, 70 plus 9 numbers.
Yeah, so is it 9 to the power 81?
But then it can change. You will never fill it up with
Yeah, it's when you talk about number of possible.
Yeah, number of possible.
I think that seems right. Yeah.
Yeah. So what this solver, Klingo and all, they're not going to compute this 9 to the power 81. I mean, that's too big a number. That's like more than the number of whatever in the universe. That's a very big number.
The question is basically like, how are we passing the input from, like, what does the neural network passes input to the Klingo listener?
That's what I'm also saying. I mean, is it? I mean,
I thought the neural network passed like a probability distribution over each of the output neurons, and I thought it just gave it that, and then it left it to Klingo to.
Yeah, I'm kind of confused there too. I mean, it's not giving those 9 to the power 81 probabilities. There's no way it can give that many probabilities.
Yeah, wouldn't it only be 810? Like, there's more than 810 unique Sudokus, but
But just say in this square, it's one of these 10 options. In this square, it's one of these 10.
I'm pretty sure you're right. Well, that's the number of output neurons.
Yeah.
But what the issue where it becomes combinatorial is in this way that fits on the board. In that the Klingo from the previous question is what it does something.
Yeah, another good point. There are 81 probabilities. Right? No, there should not be 81. 81 times 10, 810 probabilities.
Yeah. So that would be the output neurons.
Yeah, output to the neural network, right? So yeah, so this is where good. So this is where the Klingo kind of is valuable. Is Klingo is not going to compute all answer sets. Klingo actually computes the the highest one, or is able to compute, and it's not probably exact. It's able to compute a answer set and calculate its value, computes next one, and whatever time you give it, up to that time it finds the best one. I think. I doubt it can guarantee that find the highest one that quickly. But I have to ask them.
I'm sure it does.
But Klingo has a mechanism of finding.
1 year.
In the case of adding two numbers, what if we had to add three numbers? So in that case, we are only finding probability with respect to number one, I guess. So in the case of three numbers, what would happen?
So, I mean, you have to, each of the digits there'd be a probability associated with along with the operators between them.
Okay.
So you have like 5 things probability, but they'd be over different sets of elements.
So each individual probability distribution would add to one, like of number one, of number two, and of number three.
Yeah, because it's just coming from the softmax. You know that. All right, we had a question back here.
Oh, it was less of a question, I guess, more trying to reason out, get connected with the class, I guess. So the Klingo is kind of like, the way I understand it is like a probabilistic distribution of models.
So, yeah, so like, to put it in a little different terms, remember like way back, like a month and a half ago, we have the logic, we have the syntax and the semantics, right?
Yeah.
Well, with the probabilistic logic, you don't just have one model, you have a PDF over models.
Yeah.
Okay, so with Sudoku, as you can see, that PDF is over an exponential number of things. Okay, that's the 9 to the 81 models.
Yeah.
Now, what happens is this Klingo software is using some heuristic to pick the most probable model. And then it plugs that into Sudoku and sees if that gives a result. This is only on the forward pass. If the Sudoku says, oh, you violated constraints, there's no valid solution,
It passes
then it goes back, and then it goes back and it says, oh, find me the next biggest one by this heuristic.
Okay.
So that's why I asked the question earlier, because it's kind of neat that this has, the heuristic's kind of neat because it's making it easy. But on the backward pass, you don't have that luxury. You have to generate all models.
Yeah, you're not just saving the models again. You have to like regenerate. And that seems inefficient.
Yeah.
Okay, I see where we're at.
But that's why I think that other paper looks really cool that you showed.
Okay. Yeah, that one is it says the second module can satisfy these properties and doesn't. So perhaps you can I think in the last class you had PSL, probability soft logic. So the question would be, can you plug in PSL there, or what can you plug in there?
Yeah. Kusta, you had a question.
Yeah, I was regarding the toy card slide which we had. So I wanted to ask that we already have the constraints or the rules with us, and what the I'm trying to confirm whether I understand it correctly. This just says that using the rules we are helping the neural network classify. Is that what this means?
Yeah, so these rules are kind of defining when it is a toy car and when it is not. So here,
We have the rules.
Yeah, these rules are given. In this total presentation today, these rules are all written by humans. They are not learned. They are written by humans.
Yeah, the only thing we've discussed to date that generates the rules is SatNet.
Yeah.
Everything else, it assumes you have the rules. And even that, you know, this and logical tensor networks within the rules don't even have parameters, nor PSL and LNNs both do. So later we'll get into the ILP stuff where you'll actually learn the
So it's like helping, so we learn those correlational data, correlational kind of stuff. The neural network learns it from the training samples, but these rules are helping to either improve on that learning or find exceptions, like help find the exception to that, whatever the patterns the neural network has learned.
right. Like a great example was the slide with the path.
Yeah.
Yeah, because the constraints force it to have a real path. Where the CNN could just throw the first image there.
And I actually understand the training data. It's experiment.
So I mean, the training data might be. So what is the task here? Shortest path you was talking about. So imagine like you have a graph and you're trying to find a shortest, and you give a lot of examples of, oh, this is the graph nodes and this is the shortest path. This is the node, this is the shortest path, and so on. And give millions of examples and you train it. And what this is saying is that after you have trained all of that, if you just have a neural module, it can produce a sort of path, but there's no guarantee. Actually, what it means, it will produce some output. There's no guarantee that the output will be a path even. While if you have a logical module, you at least can throw out all the non-paths.
But doesn't that go against all the neural network planning solutions like with Q-learning or stuff like that? But they don't use any rules.
So, I mean, my understanding of this example is just looking at, I mean, they say MLP, so I'm just guessing they just use some best layers. So, if you're using RL, I mean, depending how you frame it, you likely wouldn't run into that.
Yeah.
Because of how the simulation works.
But even RL sometimes uses rules at the endpoint to learn Sudoku and chess-based games like tree searches, etc. Because of
That's a fair point. Another question.
So since this is separated, the two models are separated, like the symbolic part and the neural part, we could like theoretically we could do transfer learning also on this and it would work. I'm guessing.
I mean, I don't know if this has been tried with NeurASP, but a lot of people think that this is one of the values of using a gradient approach to learn something symbolic. Did you have anything you want to mention on that on transfer learning too?
I mean, the transfer learning is a little tricky in the sense the logical rules are so domain dependent. So if you are transferring to somewhere else where that logic doesn't matter, then it would not transfer. So if you are transferring to, so it depends on what you're transferring to. If you are transferring to, you're keeping the same as like, okay, MNIST addition, but instead of numbers given this way, some other way, that or some other color, maybe that's fine. But as long as, because the rules are staying there, rules are not being changed, so the particular problem has to be kind of same. The input may, you can transfer from one kind of input to another kind, but not the problem or the task, I mean.
Other questions? Okay, well then let's, any questions come online? No? All right, well, let's thank the speaker.
Thank you. Thank you for the opportunity. Okay.
Thanks much, Chitta.
Bye.